Yep. So this is the Notion page. We're using centralized Notion page to run this decentralized community calls. So today is community call number 3, which should be about AquaVM. So before we had Fluence overview, we actually, I can even see some slides. I can I think we will share this page, so you can find slides from the previous calls and also recording of the previous calls, I think on YouTube. So I think today the plan is to the Mike doing presentation about AquaVM, virtual machine that runs Aqua. And Dmitry talked about Aqua last time. And as usual, we're gonna have some Q&A, like any questions and stuff from people. And we're gonna have Juan and Joera, if I pronounce your names correct, presenting their projects. So that's gonna be interesting and cool. So yeah, if anyone has anything, feel free to tell now, or Mike also, like otherwise Mike can start his presentation about AquaVM.
Hi guys, can you hear me?
Yes.
Great, thank you. So I will share my screen. So my name is Mike, and I am doing engineering for Fluence Labs. And today I'm going to tell you about AquaVM. AquaVM is like our way to empower distributed systems. And please, if you have any questions, please ask you in the chat or just in Zoom, wherever you want. And I will try to grab them at the end of the section and answer them all. Also, at the end, we will have a short or not short Q&A section, depending on the time. So let's start. AquaVM is, as I already said, is a thing that could be considered as the heart of the Fluence network. It made complex to allow all other parts to be simple. And but before we could start to discuss AquaVM itself, let's briefly consider Aqua again. So Dmitry Dmitry covered a lot of topics about Aqua on previous community call, but now I want just to show for those who not attended on previous time, or just forgot what is Aqua and why, and how AquaVM connected with Aqua. So Aqua is our new language that is intended to run complex multi-agent scenarios across the network, especially P2P networks. And on the slide you could see. So guys, can you hear my my mouse?
We can see it, but can't hear it.
Yes, we can see it, but we can't hear it.
Yes. Okay, on the left box, we could see simple function that handles user joining in written on Aqua. So this function is a part of our simple messaging system called Fluent-pad messaging application. And this function, so the function responsible to call user list.join function. So imagine that there is some user structure, it doesn't matter how it looks like exactly, and some global app config. And this app config, there is a user list service that's identified by peer ID. And with such an operator, it allows to call a service located by such peer ID and service with such service ID that is identified on the fourth line. And on the fifth line, so user list is called, and the result obtained from user list then returned by this function. And the result here is just a simple structure that contains 2 fields. On the next slide, we could see a more complex example of a function also from this service this application. Sorry, service is a different thing now that network. And this function is intended to post a message into this chat application. And here we could see that it works with two services. The first one is authentication service, and the second one is the history service. So first of all, this function obtains a result from the authentication service and then passes to service called history. And history service, it's simple service that based on SQLite that compiled to WebAssembly, and it just adds some entry to some database. It doesn't matter, and uses this is authenticated flag to to make sure that this call is authenticated and it should really add this entry to the SQL database. And all other lines from 7th to the end of this function, they are intended to notify all users that are obtained through this list, through this function, sorry, get user list. It also doesn't matter how it looks like, but so let's imagine that it return an array of users that actually is its peer ID of peers in our network. And then it just in parallel, that it's important, just in parallel, send notification to all these users. And this one is callback on TypeScript on the browser, and also the result of history services returned. And the result here, it's also a simple structure that comprised of 3 fields. And the full example of, if you're interested, could be found by this link at the bottom of the slide. So, why I have talked about Aqua, but today our theme is AquaVM. So actually, we have complex language stack, and to execute Aqua, we have our own intermediate representation called AIR, Aquamarine Intermediate Representation. And we have a compiler written on Scala that allows you to compile Aqua code to AIR representation. And we have AquaVM that actually interprets this AIR scripts. And this AquaVM is written on Rust, compiled to WebAssembly. And thanks due to that, it could be run actually in Marine, both in Marine and in the browser. Marine is our general purpose runtime that I will cover on the next community call. So AquaVM is just an interpreter. It interprets instruction by instruction. We will look how it goes on the next slides. And the Aqua compiler has several targets. First one is to execute AIR scripts, and to produce AIR scripts directly. And second one is to produce both AIR scripts and TypeScript code. So to make it possible to run in the browser or Node.js. And on the slide, you can see the scheme, how Fluence network could be considered. So here is a bunch of nodes and relays. So actually, each node could be relay. It's it's not a dedicated role in our network. And there are 2 clients that here it's represented by browser. And on each of these actors in network, there is the AquaVM that's identified by this Aquamarine sign. Using Rust and compiling to WebAssembly allow us to run it both on clients and on nodes. So in all peers in our network. We will cover introduction, and let's take a look how AIR looks like. So actually, AIR scripts and AIR itself is based on pcalculus. So pcalculus is a special type of calculus that intended to describe some distributed systems. And actually, so there are a lot of theory under the hood. I mean, a lot of theory of pcalculus. And here you can see some extracts of the theory and some basics operators, some basic actions and combinators in pcalculus. For example, on the first line, we could see that this exclamation mark and this question mark, they represent ability to pass channel to other channel or pass name. It could be, say, it differs from paper to paper, but let's call them names. So here, for example, names could be passed to others through other names and like received from other names. Also, so pcalculus is about process communication. Actually, pcalculus is based on process calculus with several important features. And on the second line, you could see how processes could be combined to each other. So the first one means that, so this dot means that these processes could be executed sequentially. So one after other. This one plus sign represent some undeterministic choice. So either P or Q will be executed. And the last one represents like ability to start processes in parallel. And so also match and mismatch is also representable in pcalculus. And also the last thing that I should cover here is replication. So replication is a way to represent some loops in pcalculus, for example, or some recursive functions or something like that. So, for example, you know that lambda calculus could be translated to pcalculus, and some fixed point combinators could be represented through replication in pcalculus. But replication is a bit more complex than lambda calculus. Okay, let's move on and see like how all previous features of pcalculus allow us to invent AIR. So here you could see all instructions that AIR consists of. Like there are not so much of them. And almost all of them are inspired by pcalculus, except the last one called up. And all of them we will cover on next slides. So probably I need to say here that fault, also you could think about it as a about for loop, is inspired directly by replication. So all one, I think they obvious. So let's start with the call instruction. So call instruction, they're intended to call functions from services. So now it doesn't matter what the service it is. We will talk about services in the next community call. But by services now we could consider WebAssembly modules. So by such instruction we could call WebAssembly module. All instructions. So now AIR has only text representation that is based on S expressions that are inspired by WebAssembly text format. And this call consists of several parts. The first one is triplet. So this one is intended to like set a location. So first of all, it's so this one is specified where on which peer in the network which service should be called, and from the service which function should be called. So remember Aqua code that I showed previously, and then, for example, how user released service called. So this call of user released could be directly compiled into this call. So here could be like user released peer ID, this user released service ID, and a function join. So and into this function, it's possible to pass arguments. So like any set of arguments. And also a function could return a value that will bind to some name that like should be the last name in the whole call instruction. And like overall it looks like this. And from I know from a usual scripting language perspective, it could be considered as a like calling like function put from DHT service and obtain result into some data. So what is data doesn't matter now. I will tell you in the next slides. Okay, the next instruction is siku. So siku is a very simple one. it takes two instructions and executes them sequentially. So parallel is also a simple one. It also takes two instructions and executes them in parallel. So what does it mean sequentially in a parallel? It's a bit unusual. So parallel here doesn't mean that like these services could be called in different threads or some, I know, in asynchronous manner. But we will also cover this topic next slides. And also it's possible to write some lambdas to access different fields into a value. So value in our scripts, they are JSON based. So for example, this one, so this is lambda. This lambda allows you to, for example, imagine that in the script we obtain users from some user list, and this users is a JSON array that consists of JSON objects that has such fields, such field name, like peer ID, name, and so on. And this lambda allow you to choose the first object from this list, and from this object choose like value identified by such name, such field name. So it's rather simple. And app that was introduced by us to not call WebAssembly services each time, but allow to make some complex, or some simple example into your script itself. So for example, here app allows you to choose from this array the first element, then peer ID, and set it in a field called user0. So just application allows you to apply lambda. But imagine that, for example, in this arrays there is no the first field. Yes, it's imagine that it's empty. So in this case, if it's scalar, so also streams are possible. If it's scalar, there will be exception. And this exception could be catched by XOR instruction. And for example, here we could write such a script that send error to some init peer ID. Init peer ID here is a constant. Yes, so it's this constant allow you so represents peer IDs who sends the scripts. And last error is also a constant that represents object that was last error. So for example, accessing to the non-present element into scalar. And also it's also possible to check size of users by applying lambdas, and so to check it against something, there are two instructions, match and mismatched. They also directly come from pcalculus. So mismatch takes two values and compares them for equality. So a more complex instruction is a fault. So fault allows you to do iteration. Fault has so it iterates through some iterable that should be array or string, and it sets the next value into some iterator. So it's the second argument of fault instruction itself, and it executes this instruction piece. And inside this instruction, it's possible to obtain values from this iterator. And see it by example. So imagine our previous previous service called user list that provides you users in such a form. Yes, it's array of JSON objects. And the first instruction gather users and set them into users variable. And then fault allows you to iterate through, for example, so this users is a JSON object that contains users. Yes, and we use lambda to access these users. And each next user will be set into this iterator. And you could use this iterator in everywhere in the instruction inside float. For example, we could use it to obtain peer IDs from all those users and to, I don't know, to call some display message, display function. This instruction is intended to set iterator to the new element, and if it's if there are no any elements, it will pass the cycle. So just trigger the next iteration. So now is important instruction, really important instruction for code generation. So it does nothing, it takes no arguments, it's just null. Okay, it's all about instructions, and let's take a look to a particle. So particle is the core of our programming module. You could see the structure of particle on the right side, and here there are three important fields for AquaVM. It's scripts, init, peer ID, and data. So scripts is just a string representation of our script. Init peer ID is a peer ID of peer who initiated, who sent the script for the first time. And data is a special one. So we will talk a lot about data in the next section. And particles, they they travel from peer to peer, and they collect data that obtained from interpreter from AquaVM to send it to the next AquaVM. Okay, let's talk a bit how AquaVM is implemented and what is data itself. So on the slide you could see pictures that I really love. The script, this picture represents several layers in the Fluence network, especially two of them, execution layer and a composition layer. And AquaVM here on each peer, so it's inside Marine. And AquaVM, from some formal point of view, it could be considered as a state transition function, where state is data. So I will use both state and data, it is the same term. So AquaVM takes two data. I will call them, the first one is previous data, the second one is current data. So they take two data. One of them, current data, imagines that they just come from a network. So just come from particle. So I mean, it's this one, this data. And it produces a new data and a list of peer where host or peer who run AquaVM should send this new data. So it's just a finite state machine. Okay, as I said, we have two types of values. The first one are rather simple. They are scalars. They are fully consistent. They're based on a JSON. We will so JSON now I consider it as probably a good way to start. Probably we will change this format in the future, but not now. And they are consistent. It means that there is the same on the each peer in network for each particle. So in terms of one script, they're the same on each peer. And because of that, they could be an argument of any instruction, any of instructions that we will cover. And streams are rather complex. They, first of all, CRDT-like, they are locally consistent. It means that on each peer, they're consistent, they're CRDT, but they could differ from peer to peer. So I mean that, for example, on one peer, stream could contains the same values, but in different order. But this order keeping every time when new iteration of interpreter comes. But on the different peers, they could differ. They depend on a script, on a network, on some timing in the networks, and so on. They have versions in code. They call generations. They could be canonicalized. By canonicalization here, I mean that they could be they could be transfers to a scalar domain. They could be, I know, they from some special instructions that we're now in the work in progress stage. They could be from stream. We could make a scalar, and after that, the stream became consistent in the network. But without canonicalization, they could be used only by a few instructions. First of them is fault. So fault could iterate through a stream, and fault internally, like it's really complex. So it's complex when it iterates through a stream, because it should be deterministic for each time, for each run. And also stream could be used inside up as a second instruction in up. So for example, we could add to through up a value to a stream. So, okay, let's see how instructions are handled by AquaVM. So actually AquaVM treats instruction as a routed directed graph. I think it's obvious. So for example, imagine that we have two, so we have like par with two calls, and from a AquaVM perspective, it would be just a graph with three edges. And let's consider more complex example with fault. And here you can see also more complex graph that have a cycle. So this next produces a cycle from next to fault. And also like instruction could be, so it's not a binary graph, yes, because here we have fault, for example, that or match, a mismatch that has only one child, not two child. But all other instructions except call or null, they are binary. It means that they takes two instructions. Okay, and from like code perspective, so the instructions like based on a visitor pattern, and they just executed like as a tree. Okay, let's talk a bit about what parallels and sequentially means that I announced on previous slides. So on each execution, AquaVM tries to cover all, so as much vertices in graph as possible. And during this execution, Seku, XOR, and par like have different rules to execute. So for the Seku, the right subtree should be executed only after the left subgraph after left subgraph completed. So it means that all call into the left subgraph should be called, should be completed without any exceptions. For XOR, the right subgraph will be executed only if left subgraph failed with some exception. And the par always execute both subgraphs, not depending on errors, completeness of calls, and so on. So parallels here means that pars will always execute both childs. Okay, let's consider what does it mean to execute. So first of all, we don't have any saved entry point. And each time for each start, execution start from the very beginning of the script. And like in this case, we could execute some calls several times. And not to execute, we have execution trace. They stored inside data, and they they follow this graph approach, but this could be considered as a linearized graph. And from this box, you could see that we track several instructions. So par, call, fault, and up for this instruction. And for fault here, if fault iterates only through stream. For this instruction, we have evidence in a trace, yes, in the data. We have a state for them. And for example, here on the right side, you can see how state for par looks like. So just two values, size of the left subgraph and right subgraph. And for call result is enum that represent 3 states of call. So first of all, call could be like requested. So request could be sent by some peer in network, and then like interpreter obtaining such a state during execution, it understands that it shouldn't like really so call this call, yes, because this was already called by someone. Except one situation when, for example, imagine that this call was so this particle could be sent to interpreters that could really call this call instruction, because peer ID are the same. Yes, so the interpreter that runs on some peer has the same peer ID that in a call triplet. Yes, and it's first argument of the call instruction. So in this case, it will be executed. Also, call could be executed. So, and here will be a value. So the resulted value. And finally, call could be failed. And here we could see that some like exception information is also stored inside data. And like, but how calling a call instruction looks like? Actually, AquaVM could be considered as a pure function. There are no any imports to a pure. Like, but AquaVM during the during the execution of instruction, they see whether it's possible to call this, like this, to handle this call on the current PRID. If it's possible, for example, like this call or this one, then it saves all parameters, call parameters, all these ones. So arguments, service ID, function name, and tetraplet. So tetraplet we won't cover, but like they're also be tracked. And it's safe, collect them during the execution, and then provided after the end of execution as a call requests. And then after some moments, or it doesn't matter when, then AquaVM expects call results. So where there will be results of execution of this call requests. And actually there are 2 reasons to run AquaVM again and again. So first is handling a new data from a new particle that comes from a network. The second reason is to handle a call result from some service, so from WebAssembly service. And the scheme has several advantages. First one is like interpreter now. So interpreter is a pure function and it's easy to maintain. It's easy to have, I know, same binary both in browser on a node, and also it allows to asynchronous and parallel service execution on a peer. Actually, it's a pure duty to decide how services should be called. So peer has a lot of freedom in this question. And actually, execution of AquaVM takes a fixed time, comparing to, for example, having an import function that could call services like one by one, yes, and not in an asynchronous manner. It was our previous incarnation of AquaVM, but now it fully asynchronous. It's a pure function, and the scheme has a lot of benefits. And probably it has only one disadvantage. It's some overhead, because like running for each call result, it takes like some time for script parsing and so on, for data immersion. But this also could be optimized because call result could be sent to AquaVM like in a batch mode. Okay. And let's finally take a look how actually call instructions are handled. So there are 2 situations where this peer ID, they are equal to peer ID of a host where interpreter is like launch, or not equal. If it's equal, then interpreter or AquaVM collects all these parameters like service name, function, arguments, and tetraplets. and return it after the execution. If not equal, then if this execution won't execute it, so it hasn't been executed already, then next peer IDs is updated with this peer ID, and a host should send data to this peer ID then after the execution of AquaVM. Also, probably the main, the most complex part here is the merging of current and previous data that are passes to AquaVM. And why it's so complex? On the slide, you could see some some imaginary situation. When, for example, previous data has the following form. So please take a look to this par instruction. So remember, I have shown that par instruction in a data consists of two fields: size of the left the subgraph and the right subgraph. And here, so let's imagine that the size is 1 and 1. So here it means that on the left subgraph of previous data, there is one instruction, on the right also one. But when new current data comes, then the situation on the current data is different. So on the left side, both in one instruction, on the right side, there are 6 instructions. And imagine also that there are additionally 2 calls that, after merging this new or this current and previous data, could be called during execution on this peer, because data emerged, and the execution on a graph passed to a moment where this call could be called, and the resulted data that would be produced by the interpreter would look like this. So par is instruction that cares about sizes of its subgraph, and this subgraph could be longer than before, before run. Okay, and also there is also complex example with fault, but fault is much more complex than par. It won't be, so I think it's won't be covered today, but if you have any question, please ask them. I could tell you on the Q&A section. So this one is only for handling par in a call. So, and on the as the last slides, let's consider some mass point of view on the AquaVM. So from the mass point of view, AquaVM could be considered as a closed function. Closed function I here means that is functions that have codomain that is product of two sets, and the result is also set. And all domain and codomain only these 2 sets. In following Bourbaki, it's called magma. So it's just a function and a set that where function is closed. And actually it this set where x is data. So data, so interpreter takes current and previous data and produces new data. It also actually takes a lot of other arguments, but they're not so interested, not so interesting here in this context, because actually according to this set, this function, this set and function, actually it's a monoid. So monoid is an algebraic structure that has several properties. First one is it associative, and the second one is it has natural element. So it has element. So here it's empty data, and this element applying it to the data produces the same value as the second argument. I will show next slides why all of these properties matters. Now, please just take a look on all of them. And the third and fourth options are not about monoid, but the third one makes monoid non-commutative because it's important in which order data are passed. And like new data, so actually interpreter is stateless, and it saves all data it saves all state inside data that it produces as a result, and then this data should be passed as a previous data. And the last options is two idempotence properties. So okay, let's probably see how, like, why it's important. So the first one is a property of that f is closed with respect to set x, where x is all possible data. Yes, a data that consists of our all combination of our four enums. Yes, four variants of enum. So this property guarantees that AquaVM like always return data. If AquaVM is not like malicious, is not malformed, then it always return a valid data. For example, if so for this code, you could see that if some malicious data are passed to the interpreter, for example, data that couldn't be serialized, then as a result, there could be previous data itself that won't be merged with this malicious one. And if any error are produced during the execution, if, for example, current data are parsed successfully, then also like valid data will be returned in any case. The second option is really important. It's important because it allows fork join scheme in network. So this option that allows you to merge data in different order and obtain the same result. For example, it allows you to make such complex faults, because fault, especially if it's parallel, so sorry, here is SQL, but let's imagine that it's parallel. And if fault is parallel, then the result of the stream, as I already said, they could be differ on different peers. But on one peer, following this property, it guarantees to be consistent, because it doesn't matter in which order particle you come to appear. By this property, the result will be the same. So like whether it come, for example, the result of, I know, from some peer ID 0, peer ID first, it doesn't matter. The result will be the same. The third one property, there could be used to like, so remember the scheme where interpreter collects parameters of calls and produces as call requests, and then call result should be passed to AquaVM, like to set to real execute calls as call instructions. So according to this property, we shouldn't pass again and again current data. Yes, we could pass just empty data, and nothing would be changed in terms of previous data. So yes, there is some natural element that here represents as just empty data, and all will work. And the last option is the option of non-commutative. So actually, AquaVM is stateless, yes, as I already said, and it keeps all its state into data, yes, into this data that provided by AquaVM, and this data should be passed then on each new particle that come from a network. It should be passed as a previous one, so it's it should be like implemented by a host that runs this AquaVM. And it's important that this data should be previous one. So all these options allow us to, so because AquaVM is rather complex, all these algebraic properties allow us to think about some guarantees that AquaVM provides, and like allow to implement host that runs AquaVM in such a way that all these guarantees will hold. Okay, so today we covered actually like a lot of part of AquaVM, but not all. We haven't covered probably the most complex part about merging data, and like probably we'll cover on next community calls, but not today because it's really complex. And like I won't finish my talk today that I just say that AquaVM is like as I already said, heart of the Fluence network, and it allows you to run AIR scripts from that compiled from by Aqua compiler. And on the next community call, I will present Marine, our general purpose runtime that allows you to run AquaVM on these services, WebAssembly services, on a node. And all these projects, AquaVM and Aqua, they're open sourced. You could find them by this link. And actually, if you're interested in Fluence, we have several sources of updates. So first of all, Twitter, then we have newsletter and channel in Telegram and Discord with our developer updates. So if you have any questions, please contact me by email or issues in repositories or somehow. So thank you very much. I'm all and waiting for your questions.
I think we are a bit limited in time, so so maybe like if there are questions, feel free to interrupt me. If there is no questions right now, feel free to reach out to Mike in any channels. Sorry, I just muted you. Some noise. But actually, actually, I just wanted to say that like guys, feel free to jump on and present your projects.
Shall I go first? Juan, do you want to go first? Okay. So my name is Joera. I was first on the list, so I was like in my mind I've been like already. Anyway, my name is Joera. I'm a developer from Amsterdam. Normally I do like websites for editorial teams and dashboards with data. So I'm also more of a front-end guy than back-end, and all these formulas that we just saw, they make me like lose my mind. Anyway, so when I think about this new generation of technology and I think about my websites and my dashboards, I think about how can you have websites with a static site generator that is completely like decentralized, where no person can touch it. And how can I have for my dashboards, how can I have information flows of data that are not touched by any human being, and they live on these computation layers that Fluence is one of them. So for the hackathon that I just participated in, I tried the following, and I didn't. Now I'm going to look for. Oh, I think I need to share my screen. Are we prepared to do that?
You should be able to do that.
Okay. Share screen at first. Okay. Are you seeing my screen?
Yes.
Yep.
Okay. I was trying to make a data pipeline that gets data from the blockchain and posts it on IPFS. And I've used Fluence for that. And I was in the beginning, I was trying to see how far I could get, and I got it working in the end, which was a surprise to me. And I'm very happy and very positive about it. But at the moment, it's not working anymore because I started changing things and everything, so I can't demo it. But this is what I did, is that basically everything I had to do was, I did very little aqua, but mostly marine. So I made all like little services that did part of the data pipeline. So in the beginning, I have to listen to events on the blockchain. So there is like a function to call the filter, and it just checks like every minute to see if the event on that specific contract has gone off. And when it does, then it gets the ID. And with that ID, I can go to a subgraph from the graph, like this one. Oh. You see, for example, I get 18 back, and then I can get the data from the contract, like this data I get back. And then I put them in a tree on the IPFS. And so that means like it's like you make a new dark node, but you also put the nodes into the array of its parent and of that parent, and so you have like a tree. And the top of the tree, I store that. So this is all I'm doing with like creating the new leaves and storing the CID of the new leaf into their parents. And then in the end, I get basically the IPFS CID of the root of the tree, and I'm storing that on ENS. So that's about here. So I have my domain name called public record, and that's this one. So this is basically the current state, and over here, and then I can design one of the last, like basically the last one was this one. And this basically is all done with Fluence, all different marine service. So I have like here, what do I have? An ENS service, so that talks to the service, is listening to Ethereum events, and I have the GraphQL service that does the stuff with the GraphQL, and the server, blah, blah. So they're all little services, and they work together with the Aqua. So this is one where I basically just have a sequence of services running, or what I do is the WASM file of the service is on IPFS. So then first, I get that, and then I deploy it, and then I run the functions, and so on and so on. And in the end, I clean them all up again. I just remove the services again. So that's very simple in comparison to what was being discussed before. But it's been working, and that's I like that very much. Yeah, that's about it. One thing I've been doing this week is that I had one problem with the fact that when I'm talking to the ENS, I'm making a raw transaction call to the blockchain, and I need a private key for that. And previously, I had in which is, except for stupid, also not future-proof. So now I'm trying to make this sort of service that creates a private key and an Ethereum address, and then it keeps that in memory. And I use that, and it also has a sign method. So I'm first preparing the transaction, then I'm going to the service that has has the private key in memory, and signs the transaction, and then it goes back to another service, and then it makes the call. And it seems to be going to work. Yeah. Any questions?
Sounds amazing.
It's very practical oriented, and
really nice.
It mostly I didn't it's mostly been trying to learn how Rust works and what you can what sort of libraries you can use with Rust that compile to WASM, and you know, and then using the curl adapter from the Marine from the Fluence people to make these very simple calls to the blockchain, but it works, and yeah, I'm gonna keep trying. It's also very, I'm trying to figure out how to organize the workflow in a way that I can have something. I would have had something today that I could actually demo, instead of saying I changed things and I don't know if it's working. But it's very new to me, so I'm confident that it will become better.
I love the services architecture, like how you organize it as a different services. So basically, if there will be the service discovery way to like discover service by just a type or interface that you need, you would be able to just use Aqua to discover them instead of implementing them, and other people could potentially, if they exist in IPFS and they're retrievable, so other people could just take and reuse these services across the network, which is super cool.
Yeah, so I'm trying to make them more generic every time I'm looking at them. They've been very specific for this use case, but eventually there will be services that are very generic and reusable, and then people can just start piecing them together. Yeah. Yeah.
Awesome.
Okay, I think it's my turn now.
Okay. Good luck.
Okay.
Okay, that was amazing. Thank you very
much. So I stop sharing. Yeah.
Okay, I'm sharing now. I think so. Okay. Okay, perfect. Yeah, unfortunately, I will not be able to demo as well. I had a demo, but suddenly stopped working with the latest version. I had to upgrade my environment, and new version of the node is like not. I'm being able to connect, but I'm not even being able to send the messages. My name is Juan Obligado. What I did create on HackFS was a price aggregator, which processes prices from, well, any source. Right now in the demo, we were like inputting those prices manually and writing those prices into Ceramic. Ceramic then stores the stream of prices into IPFS. So I will need to go to the code as well. Sorry for that. So I do have my two things. One is my adapter to ceramic, which basically it's similar to the URL adapter that there is in the example, and instead of calling curl, it calls ceramic client. Reason for that is that in the hackathon I didn't have enough time for actually creating a native ceramic client in Rust. It's something else that I will definitely would like to do, but weren't able to do it yet. It's just having a lot of stuff to do. So we do have this ceramic adapter, which basically encapsulates the ceramic. The ceramic client utility, which is called ceramic. Ceramic is just the command for doing stuff with ceramic. So you can actually push data into a stream with that. And also we do have the aggregator itself, which is an aggregator service, which basically do have two methods. One for retrieving data. The data have the ticker of the price, open, high, low, close, the duration of the bars that we're going to have, and start time and when it was last updated. So what this code does is basically when it receives a new price, checks, updates the open, high, low, close, and creates a new bar if needed. Okay. So far, so good. Maybe, sorry if I'm going too fast. Just let me know. So here in the demo, this was supposed to, well, check the service, but and then reading the price from the bar historical prices, and then being able to update them and show them here. But yeah, as I mentioned, unfortunately, weren't able to make this work again. Well, comments about the technology, it's pretty amazing what you're doing. It's just it's amazing the pace. I think this was like 1 month ago, and the whole API changed completely in that period of time. So that was pretty interesting. The pace is going. It's a kind of difficult to keep with the pace and the app. But well, wanted to. This is more like sharing thoughts and experiences than actually making the presentation. Sorry for that.
No worries. I think it's great. It's great, Juan, that you're sharing. You know, it's important for us to hear what are the processes. You know, what were the ideas, and of course, it's like natural that code is changing a lot and very rapidly. So it's totally fine. Don't worry. Thank you. Thank you for the presentation and showing up.
Okay.
Speaking about ceramic integration, there was a bug in ceramic that we have just fixed while preparing for the ceramic workshop a couple of minutes ago. So we faced the same issue that you did yesterday and spent the whole day today fixing it. So it's absolutely not your fault, and you're welcome to the workshop, right, Bernard?
Okay, thank you very much.
I'll send you the details, Juan.
Okay.
I mean, it's probably muted, so yeah.
Okay. Hi, Bernard.
I think it's in an hour, right? The workshop. I can send the link to. Actually, we have it in the Notion. The link to the workshop today, if anybody wants to join.
Guys, may I ask you a question? Like, you have like touched marine, touched aqua, and all other stack. Have you faced any important issues and or limitations with marine, with aqua, and like, do we have something to, I don't know, to make experience much more easier for developers?
Well, it's probably the stack is pretty big. The amount of stuff that you need to put in. It was kind of difficult to like putting all together, but that was mostly my fault. Like lack of knowledge. So it's a little bit hype to just get going, because you need to put Rust, you need to put JavaScript, then you need to set up like the nodes. The nodes are very basic, so if you want to do complex stuff, you need to play with your own nodes, and that might not be that easily available. So it would be great, for example, if there was some kind of on the premises node where you can play with that. But I don't know how. Maybe that's too big infra.
My experience is very similar, and it's very there's so much. It's very complex in a way, and I don't need all the complex peer-to-peer stuff. I just had an idea of what I wanted to do, and just had to think of like what is the next step, and just only ask questions about what my next step was. And I had great answers always in the chat on the Telegram. And so yeah, I'm just discovering what my next step is, and because if I try to understand everything, then I'm gonna get lost.
Yeah, exactly. Something like that.
We found, but what interested me about the talk, and what I haven't figured out is the particles, and then like how in my workflow can I actually log or see what's in them, basically, because I'm probably using them, although I don't know I am. You understand where I'm going? Because I need to see like an object that I'm logging for me, so it can exist in my mind.
You mean that you want to for the network to be more transparent?
Well, it could be that I just haven't discovered the function of how to do it. So I mean, I've been looking. I've had the log open. You know, I always work with a local node, and I had the logs open, and so then I could like puzzle out what was going on, but to understand what the data is on the particle, that has not been visible to me yet.
Dmitry, please correct me if I'm wrong, but like when we designed all of this, we don't have in mind that user should touch particle itself in any way. It just should be, I know, as easy as possible.
Particles are also way too small to touch.
The particle data structure is very, very complicated and hard to analyze, as it's made for machines, and we are trying to make it more and more tight. But actually, I think that it totally makes sense to visualize what services were already called and what data was returned. So if we have this information, that could make the basic telemetry for particle execution. And maybe we need something like I don't know, React tooling or something like that, or a WebSocket visualization when you just can see what came when. I think it makes sense. Yeah, thanks.
So yes, some kind of profiling, for example, or something to easily show what's going on.
Yeah, makes sense.
The example with authentication, then at a certain point you can call a method, and it says like in its peer ID, it says a particle ID, it says it gives a couple of properties that are connected to the. Does that come from the particle?
Yep, from the from the service, you have access to all the fields, all the immutable fields of the particle, or you can have this access. It might be not provided, but there's an implementation detail if it's needed. It can be done. So from the service, you can access and you can know the current peer ID, which is the host ID, where the service is hosted. You know the service ID, you know the init peer ID, and for each argument, you have this security tetraplet with the sources of data that comes from the AquaVM.
Yeah, so when I log those things and I can look at them, then I get a better understanding already. When I just start thinking about it and start looking at it.
Mm-hmm. Should we describe somewhere the particle in data, or what you actually need is this tooling to visualize the data?
I don't see the tooling. You gave an example, but I don't know how that works, so I don't see it in front. I have no visual idea of what you're proposing.
Well, the idea
sure
is very similar to the Chrome tooling, DevTools. Like you can open the network tab and see the messages flying here and there. And for the particle, it's more like the WebSocket or something like that, where you have the resource with many messages inside.
Okay, yeah, but that's convenient for people that have a front end.
Yeah.
Yeah, I'm not using a front end.
And without the front end, and it could be even better, we could provide a similar CLI experience with. Yeah, I think we need to design some tool to help understanding what's going on with particles. Not sure what exactly, but we will have it.
Yeah, I saw that there is a book. Maybe encasing that book would be awesome, because all the stuff that we have in this talk is the first time that I actually saw that much information about how the VM works. Maybe updating the book, there is the Aqua book with all that would be awesome.
Mm-hmm. Makes sense, thanks. We'll prioritize.
I'm already started preparing for something else to do.
All right. I think we're out of time already, but if anyone has any topic, any other topics to discuss or any input, feel free to share. Otherwise, I think we are good.
We wanted to share some updates from the last time.
Sure, yeah, let's do it.
So let's start from my part. In the Marine stack, in the test SDK, and in the last months, we updated the Marine test macro. We slightly changed its interface, so it's more clean and logic and user-friendly. And also we added ability to use this macro with several services at once. So you can test services integration, pass data from one service to another. And we want to make more improvements later.
You can find examples in the announcement channel.
Have we shared a link to the announcements channel? Does everyone know where it is?
We did, and we will share again here.
Oh.
Cool. Nice. So the next call in 2 weeks, and the next call gonna be about what? About what?
About marine.
Okay. Yeah. Next time, marine. So we're trying to make these calls educational, but if they are too boring, let us know. We'll just talk with each other more and let's talk about the complex stuff. Right. Thanks, everyone.
Okay. Thank you very much.
Thank
Thank
you.
you,
guys. Thank you for joining.
That was awesome. Bye-bye.
Bye.
Bye-bye.